So welcome everyone. Thank you for joining us today. The SAE Detroit section and Applied Process partnered together to bring this discussion to you today. We'll be covering the advantages of Aust-tempered heat treating for ductile iron and steel, plus the advantages of replacing steel weldments with Aust-tempered ductile iron castings. Joining me today is Steve Metz, Vice President of Business Development at Applied Process. Steve will be your presenter today. For anyone who has questions throughout the discussion, please feel free to drop them in the chat box at the bottom of your screen. Please either make your comments public or send them directly to me. We will do our best to answer your questions during the presentation. If there are no initial questions, I will now turn it over to Steve.
Good morning, everybody from Oshkosh, Wisconsin. I'm Steve Metz, as Rick mentioned, VP of Business Development for Applied Process. Just a little background on myself before we get into the presentation. I'm a materials engineer by background. I've spent my entire career in the world of iron and steel manufacturing. I was in the foundry industry for 20 years. Prior to joining Applied Process, which does heat treatment of steels and irons, and I've been with AP for 9 years. I start out with an apology. My child is a Labrador Retriever, and she's in the house here, so if you hear something that sounds like Chewbacca in the background, it's Sadie, just wanting to go outside. Also, this is 8 hours of typical education boiled down into 1 hour. So this is just, to whet your appetite a little bit and introduce the topics. So with that, I'm going to stop my video and start presenting. So very quickly about Applied Process, we are the worldwide leader in Aust tempering, which is quenching in molten salt from a heat treatment perspective. It's all we've done since 1982. It's the only thing that we do. We do not do oil quenching, water quenching, induction, or other types of heat treatments. We focus on one thing. When it comes to metallurgical and materials engineering bench strength, it's truly humbling. We have 7 materials engineers or metallurgists within our company of 140 people. We like to call our plant state of the science. Sometimes metallurgy is considered an art, but we consider it a science, and our facilities are clean, safe, and efficient. We do have locations in Livonia, Michigan, just outside of Detroit, Oshkosh, Wisconsin, where I am located. I used to manage that facility, and Fort Smith, Arkansas. As far as our quality systems, our 2 facilities that are not automotive related, which would be Oshkosh, Wisconsin, and Fort Smith, are ISO 9001:2015. And because of location and industry served, our Livonia facility is IATF. And what do we do? 95% of our business is derived from converting components from one material and process type to the other. That's why we're so technically heavy in the materials and metallurgy side of things. And we're part of a much larger company. We're part of Alberts, which is it's based out of the Netherlands, and that acquisition happened in 2019. So the molten salt quench process, different products come from that. So there's Aust-tempered ductile iron. You can do Aust-tempered steel, Mar-quench steel, Carbo-Os tempered steel, where you're actually laying case down and then doing the molten salt quench process. We do a unique material primarily for the agriculture and construction and mining industries called carbidic Aust-tempered ductile iron. It has extremely high hardness and good wear properties. You can Aust-temper gray iron as well. And this just shows the different industries that utilize salt quenched product, and this is just on a percentage basis. And what I'm trying to show here is those industries that have adopted or are adopting this technology. And agriculture, we've done a lot of business with them over the years. The interesting one to look at, though, is light vehicle, and take a look at how, from a percentage wise, that industry is growing dramatically. And that's primarily being driven because of lightweighting of components. And in order to lightweight components, you need to make them stronger. So why do we heat treat parts? The advantages are you can improve the strength, you can improve the wear resistance because of the increased hardness. And because of this improvement in strength and or wear resistant, it allows you to reduce the weight of the part as well, which is an extremely important attribute, especially in the vehicle world. The disadvantages of heat treatment is it can reduce the toughness and strength as the hardness of the material, as strength and hardness increases. Then the interesting thing about molten salt quenching or Aust tempering is it minimizes this reduction in toughness. So it retains a higher level of toughness than if you were to process parts through a traditional heat treatment process. And interesting enough, we'll talk about Aust tempered ductile iron. It both increases the strength and the toughness of the material. So metallurgists, we like to use words that confuse people, but really it comes down to it's about creating a preferred atomic crystal structure. And these are some of the words that we like to use: body-centered cubic, face-centered cubic, body-centered tetragonal, lamellar, acicular, ferrite, pearlite, martensite, austenite, iron carbide, Aust ferrite, Bainite. All words, but all they are is a different crystal structure. So my wife is an interior designer. She uses the opposite half of the brain that I do. And when I started working in the world of heat treat, she said, "What do you do?" And I said, "We rearrange atoms for a living. That's what we do." And she didn't understand it. So I went through the periodic table of elements and I came across carbon. And carbon has two predominant crystal formats: hexagonal close packed, which when the carbon atoms are in that format, you get graphite. Graphite is soft, it's dark in color, it's got good lubrication properties. If you expose carbon to extremely high pressures and temperatures for an extended period of time, you can convert that crystal structure over to diamond cubic. That is a different crystal structure of carbon, has completely different mechanical and physical properties. And as I mentioned before, in the world of heat treatment, we're trying to create a preferred crystal structure. My wife was very quick to point out that her preferred crystal structure for carbon is the diamond cubic structure. Common heat treatment processes that are out there: you can heat parts up before you quench them in a controlled atmosphere, or you can do it in open fire in the presence of oxygen. There's oil quenching, which is probably the most common type of heat treatment that's done, and you have to come back and temper the parts. There's water quenching and tempering. There's polymer quenching and tempering. There's carburizing, where you enrich the surface of the part with carbon to improve the hardenability and hardness. There's nitriding, where you do where you add nitrogen to the surface of the part to increase the hardness. You can do vacuum heat treatment, flame and induction. And then there's this unique thing called salt quenching. And through that process, you can do Aust tempering, Mar quenching, Quench and Temper, Carbo-Os Tempering, different things. So some people may not have seen what heat treatment is about. And so you can find anything and everything on YouTube nowadays. So I just went and picked some random videos. These are some gears that were carburized and are going to be quenched in an oil tank. So heat treatment of steels and irons starts by heating the parts typically in that 1550 to 1700 degree Fahrenheit range. So here we can see some parts over an open oil quench tank, red hot, about 1550 degrees Fahrenheit. Now, the interesting thing about this is that the parts are oxidizing and they're cooling at this point in time. So that's actually something bad when you come out into open atmosphere. And as the parts hit the molten, or as the parts hit the oil, you will see flames erupt. Another common heat treatment method would be water or polymer quench. And again, this is the parts are being taken out of an open fire furnace. These parts are stainless steel rings that are being solution annealed. They're about 2100 degrees Fahrenheit when they come out of the furnace in this case. And then they're transferred to a quench tank. This is a polymer quench tank. And you'll see that the part rapidly cools off. So heat treatment is doing that. It's heating the part to a temperature and then cooling it either rapidly or in a controlled manner to get a preferred crystal structure. That's what heat treatment's about. So for engineers who might be on the line, this is what's called a Ttt diagram or an isothermal transformation diagram. This is a roadmap to microstructures. I hated these back in college, and now it's the world that I live in. But what this tells you is when you go from left to right, that's time, and on the vertical axis or the y-axis is temperature. And there's different phases. There's gamma, which is face-centered cubic iron. There's F, which is ferrite, which is body-centered cubic. Pearlite is another structure. It's a lamellar structure of ferrite and iron carbide. And you can take different paths through this diagram and you get different crystal structures. Just like if I live in Oshkosh, Wisconsin, and if I wanted to get to Detroit, there's different ways that I could take. I could drive up through the UP, I could drive through Chicago, or I could fly from Appleton to Detroit direct. Different ways to get to a different place. So let's take a couple of journeys through this. If we start with steel at about 1600 degrees Fahrenheit and we slow cool it, you get a ferritic structure, and that would also be called annealing. So that's a heat treatment process many people are familiar with. You could cool faster by perhaps using fans and air cooling, and you get a pearlitic structure. Very common processes are quench and temper. So we could start at that same 1600 degrees Fahrenheit, quench the part in oil or water, and you cross these lines called martensite start and martensite finish. So you form what's called martensite, and you have to temper that. That's tempered martensite. And then there's what we do in the world of molten salt quenching. And that is you still start at 1600 degrees Fahrenheit, but because we're quenching in a molten salt bath at high temperatures, we get a different structure. And in steel, it's called Bainite. And Bainite has some unique mechanical properties. So again, we elevate the component to about 1600 degrees Fahrenheit would be typical. We quench it, but then we have to hold it while the microstructure develops over time. That's a little bit different than oil quenching or water quenching, which is you quench it, you take it out of the quench tank, you temper it, and you're done. So this is a time-dependent process. So what makes austempering unique? It avoids the formation of martensite. Martensite's brittle, and it causes distortion because it is a what's called body-centered tetragonal microstructure or crystal structure. Oil, water, and polymer quench are all going to form martensite. Austempering quenches the parts in a 50-50 mix of sodium nitrite and potassium nitrate is typical, which is first liquid above 310 degrees Fahrenheit. So we're quenching at high temperatures. You know, if you think of how hot can you get water, it boils at 212 degrees Fahrenheit. Oil starts to become unstable above about 300 or 350. So relatively low temperatures in comparison to what we can get to with quenching in salt. And then austempering allows for quenching above what's called martensite start temperature. And then we hold it there while this preferred microstructure called Bainite in steel or Aust ferrite in ductile iron develops. So we're going to talk a little bit about aust-tempered steel. Tagline is toughness at high strength and hardness. And first thing we do is we go to a microstructural. This is a fracture surface of a tempered martensite, so something that would have been oil or water quenched and tempered at 53 Rockwell C. This is what's called a brittle fracture. If we look at the same steel, I believe this was 1074 steel. Oh no, there was 10B53 that was aust-tempered to 53 Rockwell C. Notice the morphology of the fracture surface is much different. This is a dimpled or a ductile fracture surface. And that's all because of the difference in crystal structure of the parts. So that's why this difference in fracture mechanics is why there's better mechanical properties in bainitic steels. I'm not going to dive too much into this. You know, again, there's this great equation down at the bottom, but the hardenability of a steel, so the hardness level and the depth that you can get the hardness and the strength into the part is a function of the chemistry. And I'm going to show some Ttt diagrams on the next few slides. We can have lots of discussions at any point in time about Ttt diagrams. What I'm trying to show here is that depending upon the chemistry of the steel, the Ttt diagrams change. So either the hardness of the material and the strength of the material changes, and also the thickness that we can through harden also changes. So chemistry is very important in the heat treatment of steels and irons. For example, there's very little that can be done with 1020 steel because there's so little alloy in it. But 4340 steel, you can do a lot with. It has high hardenability. You can through harden heavy sections. So I'm just going to page through some of these. You can just see how the Ttt diagrams change with changing chemistry. Let's jump into some of the mechanical properties. This is what a lot of engineers are interested in as well. So this is a 1074 steel, Aust tempered, Bainitic, versus oil quenched and tempered martensitic at the same hardness. The Bainitic steel exhibits a higher tensile strength, a higher yield stress or yield strength, and look at the difference in elongation. That is one of the key things. So it's about, it stretches before it breaks about 6 times the amount of an oil quenched and tempered steel at this hardness. And that results in a dramatically improved impact strength, energy absorption. Recently, we did a test on 10B38, which is about the lowest carbon and alloy steel that we can effectively Aust temper. We Aust tempered the part to 45 Rockwell C, and we had just some amazing mechanical properties. And I just noticed an error on my table here. The tensile strength in KSI was 220. The yield strength in KSI, not megapascals, is 200 KSI. And it had 14% elongation before it failed. So the energy under the curve, or the area under the tensile curve, was dramatic, which relates to the energy that the part can absorb. We can also do Carbo-Os tempering of steels, which we'll talk about in a little bit, and a similar thing happens. So when you add carbon, you can improve the hardenability of the material and the hardness, and you can get to extremely high mechanical properties in comparison to oil carburized and oil quenched and tempered. And this just shows you the tensile strength improvement. The unnotched Sharpie increases by over a factor of 10. The elongation increases at essentially the same hardness. There is a limitation. We're talking about 40 Rockwell C or above. So fairly high hardness. That is when Bainitic steels are better than martensitic steels. One of the other aspects that we have found highly beneficial to the salt quench process is reducing distortion. And I could get into the microstructural reasons, but you can see here that the linear transformation expansion of Bainitic steels is dramatically lower on a percentage basis than 100% martensitic. Anecdotally, I can give an example. I can't show this, but I can talk about it. We had a customer approach us. It was a pump shaft, 18 inches long, 3/4 of an inch in diameter, and they were trying to hold 5 thousandths of runout over the 18 inches. And they were oil quenching and tempering the part, and they couldn't hold 30 thousandths of runout. We successfully Aust tempered the part and were able to hold it within 5 thousandths of runout. So, and it's because we're creating a preferred crystal structure that does not distort as much. So where is Aust tempered steel used? Most people actually come in contact with it every day in your vehicles. There's a lot of Aust tempered clips and clamps. Seatbelt components are oftentimes made with Aust tempered steel. Horizontal boring bits, seat brackets. Years ago, I don't know if this is still the case, but the ribs and the crash test dummies used to be made out of 1080 steel that was Aust tempered. Heavy duty springs can be made out of Aust tempered steel. Water pump bearing races. We do a lot of work in the roller bearing industry, and we're talking about 50-100 steels typically that have hardnesses in the range of Rockwell C 50 or 60, and very minimal distortion at the same time. So we can get, even in salt quenching, we can get to some extremely high hardness levels. This is an interesting product. These are sheet metal shears. The blades are 1075 steel or 1095 steel that has been Aust tempered. The reason for that is when you're cutting other metals, you don't want the blades to chip, and these will not chip typically. This is a very interesting component as well. These are sewer cleanout blades. These are 1075 steel as well. The reason they Aust temper these is, again, it's because of that high level of stretch before the material breaks. So the worst thing that could happen on a sewer cleanout blade is for it to fail when it's doing its job. So what they do is they Aust temper the steel, and if they hit something that's immovable, the blade simply coils upon itself and does not break. We do quite a few gun components as well. Again, low distortion and high toughness. Just about every lawnmower blade, either the typical rotary lawnmower blade or for turf care for like golf courses, etc., will be made through the Aust tempering process. On the lower right, you see what's called a bed knife. That goes on a real type, mower that would be used on a golf course. At 48 to 52 Rockwell C, we can take one of those bed knives, put it in a vise, and bend it at 90 degrees, and it will not break. If it were to be oil quenched and tempered to the same hardness, it would break probably at 15 to 25 degrees of bend. That's the thing about these blades. You do not want them to shatter. You want them to distort and absorb energy. Perforation tines are also primarily made out of Aust tempered steel. These are steel tubes that are used to make nightsticks for police. In the old days, they used to use wooden billy clubs or nightsticks. Now they use telescoping 2 or 3 piece tubular type. These will not break. Just a word of warning to people. Another example, this is an 8640 bolt that we Aust tempered to 44 Rockwell C and then bent it to 90 degrees. If this would have been quenched and tempered, it would have broke. So the advantages of Aust tempered steel. I cannot recall an Aust tempered steel part that we cracked in our process. If you quench a part in oil or water, you have to come back and temper it quickly afterwards, otherwise it can crack all by itself. Less distortion, talked about that. Higher yield strength, increased elongation, increased wear resistance because the matrix is just more difficult to rip apart. Greatly improved impact properties, and then increasing fatigue strength up to maximum Bainite hardness. I had mentioned another process that's called Carbo-Os Tempering. So in the furnace, we can process the parts at temperature and have a high carbon potential in the atmosphere. And what the carbon then does is it works its way into the steel over time. So you have, imagine this was 4140 steel and it was carburized. So there, instead of being 4140 on the surface, it might be 4180 steel. So it's got a higher carbon content. So you can get a harder surface and a softer core. So you can have good wear properties, but have good toughness because of the softer core of the material. This almost is a composite material. This plots elongation versus Rockwell C hardness, and the carburized, quenched, and tempered is the curve with the triangles, and then the squares is Carbo-Os tempered. So what we have is for higher hardnesses, we have higher percent elongation, which yields to higher toughness. Examples where Carbo-Os Temper has been used, output shafts on transmissions, another transmission output shaft, another spline shaft, a differential cross, clutch spring plates, starter clutch cells. And if anybody on the line has owned a General Motors pickup truck with an Allison transmission in it behind the Duramax, there's a Carbo-Os tempered parking pawl in it. Scroll compressor U-arcs. So the advantages of Carbo-Os tempering, again, it's very similar to the Aust tempering of steels without the use of carbon. It's no cracking, less distortion, higher tensile strengths, increased elongation, increased wear resistance, greatly improved impact properties, and increased fatigue strength as well. So our next topic, this is the world that I lived in for many years, is the production of ductile iron. So you can take as cast ductile iron, which is widely used in many industries, and you can Aust temper it, and you get an Aust ferrite microstructure, which then makes it Austferritic ductile iron. It's also known as Aust tempered, or ADI for short. So, this material can have 3 times the yield strength of as cast ductile iron. So you can take an engineering material that it has fairly good mechanical properties and dramatically improve them through heat treatment. And there are examples, I can't show them here or share them, but we have replaced aluminum components at equal weight. And that is huge because you're dramatically improving the strength of the material, now you can take mass out of the component. And a material that's lower in cost than aluminum, steel, forgings, castings, and weldments. ADI is that material. I like to pull examples from different industries. So this is a re-railer that is used only when just the wheels go off the track in the railroad industry. And the challenge they had is this part weighed 142 pounds when it was made in cast steel. And because it was 142 pounds and there's a 50-pound max weight limit for lifting, it was a 3-person lift to get these re-railers into position. They decided to utilize the strength of Aust tempered ductile iron, or ADI. They were able to get the weight down to 97 pounds and it made it a 2-person lift. This was the first test that was done on these components back in 2012. So this is a 200-ton 6-axle locomotive that they purposely derailed. The wall thickness on these castings is about 5/8 of an inch thick, and on the inside there's a series of gussets to improve the load carrying capacity. So they use finite element stress analysis to understand how to optimize the design of the component. And the key on this particular, this portion of the video is watch the last wheel hit. It takes a significant blow right at the end there. So we're going to start with a general discussion of the different iron types. So gray iron, oftentimes used in brake rotors, for example, is the graphite, which are those, is in a flake format. Those are the black lines there. It typically has fairly low tensile strength, 20 KSI to 40 KSI is typical. When the graphite shape changes to worms, that's called compacted graphite iron. Look what happens. The mechanical properties start to improve a little bit. Now you get 40 to 60 KSI tensile strength. Years ago, they used to make what's called malleable iron. It requires a heat treatment to get the graphite into this shape. But again, as the graphite shape turns from flake to more round, the mechanical properties continue to increase. And then 1942, somewhat by accident, ductile iron was invented through the use of a magnesium addition. And ductile iron can have strength 60 KSI to 120 KSI, which is strong, but still not as strong as some of the steels that are out there. But if you Aust-temper it, you can dramatically improve the mechanical properties further, essentially doubling or tripling the strength of the material. Again, you increase the strength. Now you can decrease the weight of the component if the load carrying capacity is increased. So again, we go back to the IT diagram or the TTT diagram. This one is for ductile iron, though. This is a generic diagram we use to explain the process. So if you slow cool ductile iron, you get a ferritic structure. So that's annealing. If you fast cool with air, you get a pearlitic structure. If you rapidly cool using oil or water, you get a martensitic structure. And again, you have to temper it. And then there's austempering or molten salt quenching. Again, we quench at a relatively high temperature, and we hold until we produce this structure that's austenite and ferrite, or Aust ferrite, and there's the microstructure. So all we're doing is this, again, it's the preferred crystal structure by taking a different path through the TTT diagram. This is the ASTM A536 ductile iron specifications for as cast and for quenched and tempered. And there's 60-40-18, 65-45-12, 80-55-06, 170-03, and 120-90-09. And I shaded the 120-90-09 because typically that is quenched and tempered to get to those mechanical properties. But as you can see, the interesting thing is, as the tensile strength increases from 60 to 65 to 80 to 100, look what happens to the elongation. It drops. So that's the amount of stretch that the material has before it breaks. And so increasing strength decreases the elongation, which is bad because you're reducing the toughness of the material. So this is a powerful example of, you can take 80-55-06 ductile iron, which is probably the most common grade of as cast ductile. If we were to Aust-temper it, we almost double the tensile strength. We double the yield strength. The elongation actually goes up from 6% to 7%, and then the unnotched Sharpie impact more than triples. And again, the reason for that is we've created a different crystal structure in the matrix of the material. There are 5 grades of ADI. 1, 2, 3, 4, 5. This is something that the metallurgists actually made fairly simple to understand. And grade 1 and 2 are typically going to be used in applications where toughness is important. So control arms, knuckles, components that take a shock loading are going to be made out of grade 1 or grade 2 ADI. And there's ISO standards as well as ASTM standards for this material. Grade 4 and grade 5 are higher strength, higher hardness materials, but again, the toughness is lower. Where do we see grade 4 and 5 used? Construction and mining, agriculture. So like ripper points for tilling up a farmer's field will be made out of grade 4 or grade 5 ADI. So what is the raw material for Aust-tempered ductile iron? It starts with good ductile iron. So we have a couple of sayings internally. Aust-tempering can make good iron great, but it cannot make bad iron good. And you can't make chicken soup from chicken poop. So in order to produce good Aust-tempered ductile iron, you have to start with a casting made out of ductile iron that is of good quality. And just some guidelines on that. It has to have consistent chemistry, just like with steel. If you buy ductile iron with consistent chemistry, you will get good results. And you also want, you see these, the black dots. This is a photomicrograph taken at 100x. Those are the graphite nodules that during solidification appear or come about. And we want lots of those nodules. So we want a minimum of 100 of these little graphite nodules in a square millimeter. And then we want those graphite nodules to be extremely round. Those two attributes help produce good mechanical properties as an end result. And also it helps us aust-temper the material to get it to better mechanical properties. And of course, you don't want other stuff in the matrix. You don't want carbides, inclusions, porosity, or other things. So good quality ductile iron is important. There are, the wonderful thing is there's many good quality ductile iron foundries in the United States. And I'm going to call it, we know where the Rust Belt is. It kind of starts in the Twin Cities, runs through the Oshkosh, Wisconsin area where I live, down through Chicago, Detroit, and then out to the west or the East Coast. Again, as I commented earlier with steels, aust-tempered ductile iron is very consistent in its growth. And we actually have a table that we developed that says, you know, if you're going to produce a part to grade 1 ADI, and it's going to be a ferritic structure when we get it, it's going to grow 1.2 thousandths of an inch per inch of dimension. About 40% of the parts, aust-tempered ductile iron parts that go through our facilities come in pre-machined, either finish machined or rough machined, and then maybe they might have to just touch a few things up after. So consistency in that growth is very important. So again, the steps in the aust-tempering process, we start at room temperature, we elevate the part to about 1600 degrees Fahrenheit would be typical. We hold for a period of time while carbon actually diffuses out of the graphite nodules and into the matrix. And then we quench. Again, we're quenching in molten salt, so we're at high temperature. And if we quench up around 700 degrees Fahrenheit, pretty hot, we get grade 1 ADI. And you can see what the microstructure looks like there. It's that acicular or needle-like structure. If we follow the same path, but we quench at a lower temperature, we get grade 5 ADI, which would be used in the agriculture or construction industry. And it has a hardness of 402 to 512 Bernal. So just we can take the same part and by quenching it at different temperatures, get to the different grades of ADI. That's how it happens. So this is what an as-cast ductile iron microstructure looks like. You can see the graphite nodules. It is surrounded by ferrite that's white, and then the kind of medium gray color in between is pearlite. This has a hardness of 187 to 255. This is the most common grade of as-cast ductile iron. After aust-tempering to grade 1, the structure changes dramatically. Note though, we do not change the graphite nodules, even though there might be a different quantity of them. This is a different sample, but everything else in between the graphite nodules changes. It's that Aust ferrite or acicular structure. And then that's what grade 5 ADI looks like. It's a finer structure and a slightly different combination of austenite and ferrite. This is a powerful chart. This plots for various materials yield strength versus percent elongation. And the pink zone on here is alloyed and hardened steels. The blue zone is ductile iron. Notice they don't overlap a lot. Ductile iron does not compete with steel on a regular basis, but when you aust-temper it, aust-tempered ductile iron can occupy a big portion of this yield strength versus elongation space. So it can replace steel, and we'll talk a little bit further on in the presentation about castings and some examples of conversions that have happened. The other nice thing about ductile iron and ADI is by switching your part maybe from carbon steel to ductile iron or ADI, you get an immediate approximately 10% reduction in weight, and that's due to the graphite nodules that are in the part. Another interesting facet of Aust-tempered ductile iron is when it is exposed to a yielding force on the surface, such as shot peening, or if it's an agriculture tillage point that is being dragged through the ground, it strain transforms on the surface and the hardness goes up to 50 to 60 Rockwell C. And that is a self-renewing surface. So as the wear continues to happen, the material underneath continues to strain transform or harden to a depth of about 1/2 of a thousandth of an inch to 1/1000th of an inch. And then if you shot peen ADI, you can put a significant residual compressive stress on the surface that is also due to this, this phase transformation. This chart is more for probably for the agriculture industry and construction and mining, but Aust-tempered ductile iron does fairly well in wear performance in comparison to as cast irons or abrasion resistant irons. So as cast irons are going to be in the upper left, and abrasion resistant irons, which are going to be like 27% chrome white irons, NiHards, are on the lower right. ADI is machinable because it has higher mechanical properties. It is more difficult to machine than as cast ductile iron. We often tell people that it machines about the same, grade 1 ADI machines about the same as steel at a similar hardness. So what's the economic driver behind switching parts from, say, a fabrication or a forging to a ductile iron casting that's Aust-tempered? Because ADI increases the strength of the material by 50 to 100% or more, now you can reduce the part weight. And that is where the power is. It's design optimization. Ductile iron costs typically, it varies a little bit, but 90 cents to $1.75 per pound. And if you can reduce the weight by 25 to 33%, now you can come back and Aust-temper the part and have a net neutral part, perhaps, as from a cost perspective. You can have improved performance due to the extended wear life, reduced total downtime due to, or total cost due to maintenance, downtime reduction. And there's not a lot of steel foundries left in the United States. We used to have this question more often, but people have migrated to ductile iron castings because there just is not a supply base in the United States for steel castings. So why convert fabrications to castings? You can increase product performance, which could be wear resistance or strength. Because of the improvement in strength, now you can reduce the weight. You can reduce the number of components. If you have a weldment that is, say you have a 5-piece weldment, you can convert it into a 1-piece casting. And we've got some great examples of weldments and fabrications converted to castings a little bit later. Reduce total labor cost, and this is becoming more and more of an issue as the labor market tightens in the world of metals manufacturing. Welders are very hard to find. And aesthetics. A well-designed casting can look beautiful. You can put your logo on it, for example. It's more flowing, and you'll see some side-by-side comparisons in a bit here. There are a lot of tools that exist today to aid in the casting conversion process, and there was a couple of questions that came in just before this presentation, so I added this slide at the last minute. There are solid modeling programs, SolidWorks, ProEngineer. There's lots of them that are out there. Those didn't exist when I first came into the foundry industry, or they were just starting. So these solid modeling programs, many of them have built-in features for finite element stress analysis. So you can understand how your part performs as a ductile iron or an Aust-tempered ductile iron component by using the FEA package that's built in. Many of these packages also have parting line analysis and draft analysis so that you can help the foundry design your part. There's a new technology that's out there. It's 3D printed sand molds. This has reduced the time to market because you can make a prototype casting without a pattern. Typically, if you're going to make a ductile iron casting, you would have had to make a pattern. There's an expense associated with that. Then you have to make the mold, pour it. Well, you can now take your solid model and you can turn it directly into a 3D printed mold that can be poured by just about any foundry. And that's direct printing of these sand molds. The question that came in before this was, what is the state of the industry relative to mold flow and solidification analysis? And I had actually the experience of back in the early 90s using one of the first solidification modeling packages that was available. And the technology has come a long way over the last 25 years. So it's finite element and mold filling and solidification. So even before you make a pattern or make a sample part, you can understand how it is going to solidify. And if you design the gating system, you can do the mold filling at the same time. There are many packages that are out there for this type of analysis. Probably the most common ones are Magma, M-A-G-M-A, and I think there's one called Nova. There's also one that I used back in the early 90s called Procast that I believe is still out there. But they're commercially available. There are a lot of parameters that have to be put into them. And I will say that most foundries do have this software already. It helps them because they don't have as many iterations going from the design phase into production. I want to walk through some examples of components that either have converted to castings or maybe are in the concept stage. And I want to talk about some of the items. So this is a tow hook for a vehicle. This is something that that we actually designed, and we took it to the OEM. And it was a great concept. It was a cost reduction. It was a weight savings, but it was the wrong time. We were just after the launch of this particular vehicle, so it was a non-starter. They weren't going to change anything for 3-4 years. So understand the timing when you're converting something to a casting is important. If you want to reduce part count and labor hours, castings are a great way to do it. This is what's called a spring pack. This is on a piece of agriculture tillage equipment. So completely different industry. But what this does is if a farmer is tilling a field and they hit a rock or an immovable object under the soil, the spring and this allows the ripper point to pivot up out of the soil and then come back down in after it's cleared the obstacle. On the left, you see the weldment, and on the right, the components were redesigned as 4 ductile iron castings. So you went from 40 pieces welded together to 4 castings. It was a 63% cost reduction. And then, there were some design modifications. And if you were to look at this is just this is the solid model, but the customer did put their logo on the side of the J portion of this. So that's where I call it aesthetically, it can be much more pleasing. This is a 37-inch diameter track drive wheel that was converted from, I believe, 44 pieces of steel welded together to a 1-piece ductile iron casting. And it also does get heat treated. It gets aust-tempered afterwards. This is a project that there was a senior design project at the University of Michigan. And they took a tow hook from a vehicle and they said, let's see how we can lighten this up by turning it into a casting, by putting the metal where it's needed, and then aust-tempering it to improve the strength. Now, this was just a concept. This was presented to the OEM. They do have a copy of this sitting on one of their desks, but it resulted in a 56% weight savings at the same strength level. And this particular class estimated about an 11% cost savings. They went out and had some quotes done, and that was their estimate. This is another example from a few years ago of this same senior design class. It was a control arm that was converted from a multi-piece stamped weldment to a 1-piece ductile iron casting that was then aust-tempered. It was about a 9% weight savings and a 12% cost savings. Some other examples of historical aust-tempered ductile iron parts. From 1977 to 1979, many of the pinion gear sets in rear drive, mid-size vehicles were made out of Aust-tempered ductile iron. Limited slip diff cases, timing gears for diesel engines. This is a 3-piece fabrication that was converted to a 1-piece ductile iron casting that then gets Aust-tempered, and it comes to us pre-machined. So it's complete. That's a testament to the stability of the Aust-tempering process. These are very large planet carriers for mining dump trucks. These come to us rough machined and finished machined. So there are certain features on these that are pre-machined to the finished dimensions, and there are certain features that, just because of tolerances, need to be finished machined afterwards. The one thing we do have to watch out for in larger castings that are what we call rangy is the solidification stresses that exist in the parts prior to Aust-tempering. We relieve them. Heavy duty air suspensions for trucks. This was a steel forging that was converted to 1-piece grade 2 Aust-tempered ductile iron casting. These are spring hanger brackets for heavy duty trucks. Steering knuckles, these are, I think, from the 1990s, this particular one was. Another example of an agricultural component that was converted from a steel weldment, 15 pieces, to a 1-piece ductile iron casting that was then Aust-tempered. Again, look at the aesthetic difference between these two components. The welded component is on the top, the casting is on the bottom. So it was a 25% cost savings, a 9-pound weight reduction, and an improvement in strength, alignment, and everything else. So there was a lot of advantages to doing this conversion. On the back of tractors, the J hooks for 3-point hitches are oftentimes made out of Aust-tempered ductile iron. There were some very unique design considerations done here. Notice that the inside of the J hook is hollowed out. They put the material where it was needed. And also on the bottom of the J hook, it is scalloped out to reduce mass and section size as well. So this was lightweighted. If you're driving down the road and you see a tandem trailer truck, the pintle hitch in between is usually made out of Aust-tempered ductile iron. Tow hooks on light vehicles have been made out of Aust-tempered ductile iron. And this is an 84-piece fabrication assembly that was converted into a 1-piece casting. Weight was reduced by 15%, cost was reduced by 55%. This is a planter boot for the agriculture industry. That looks like my welding on the lower right. It was, it's ugly. And then look at the aesthetics of the casting on the upper left. So what does ADI offer the end user? High strength to weight ratio. Again, we mentioned it can replace aluminum pound for pound, good wear resistance, good fatigue strength, good manufacturability, because you can make the part net shape. Because you start with molten metal, you can flow it into a sand mold that has the material where you need it in the casting. Low product cost, lower cost than comparable steel or aluminum components, and again, this lack of the steel base in the United States. The other thing that and the reason why we're here today is about education. Castings and heat treatment are difficult topics to understand. And again, we've condensed probably 8 hours into 1 hour of presentation. But if there's additional needs, we can custom tailor education about casting design, basic heat treatment, Aust-tempering, and we can do these virtually at our facility or at your facility. Again, what we found is that educating the customer, educating design engineers improves the metals manufacturing industry in general. And other resources that are available, we have a website. All of our contact information out there is, and we have a technical library that talks about all these different heat treatment processes that we've discussed and the applications in different industries. So with that, I have concluded my presentation and pretty much right on time.
Thank you, Steve. Very informative session. To wrap up this discussion, we would like to thank you all for joining us today. If any additional questions come to mind, please contact Steve or me via the information displayed after we close. If requested, we will tailor a presentation for any special requirements or challenges your company may have. The full video of this presentation will be available on the SAE Detroit section's YouTube channel. I would also like to remind everyone to review the list of upcoming events at the SAE Detroit section's website. Thank you again and have a great rest of your day.